start recording. I have started recording. So we are super happy. Start very soon. I don't know. I can hear myself. I hope it's not happen. It's not going to happen any longer. Okay, this is because of Sergio. Thank you, Sergio. So people, I remind you to turn off your microphone. So we cannot have a better start. Andy Cohen will lecture us old school with Blackboard, which is something I particularly enjoy. And this is, there is no more I can say. I handed the session to Andy. Andy, when you are ready, you can start.
Okay, let's see if this technology will cooperate. Okay, I think I'm visible. Is that true?
Yes, you are. Yes, you are.
Okay, excellent. So I can see no one, so I get no feedback. I assume that there are people actually listening aside from Sergio and Gabriela. Is that true?
Yes, you can see there are a little over 70 people connected. So there is a lot of audience.
Okay, terrific. So first, let me begin with an apology, which is I am not particularly adept at giving lectures in this very odd way where I stare at a camera lens and get no feedback from an audience. And I am accustomed to not using prepared slides, but writing as I speak, which is always a challenge given that I'm writing on this tablet. So I'm sure all of you are familiar with this by now after a year and a half of this unprecedented situation, and I'm sure that you will be charitable and forgive me if I'm not my usual bubbly self. I wanted to point out that the Standard Model has a long and illustrious history with thousands of pages having been devoted to its explication and illumination. In light of this, all of you, and particularly myself, might rightly question what value we may find in my delivery of 3 brief lectures on the subject. And I can assure you that if you are somewhat concerned about what this will be like, I am far more so. And that worry has led to quite a few sleepless nights and a not inconsiderable increase in my weight from all the ice cream and alcohol I have ended up consuming with that worry. So in the end, I decided to do something maybe a bit different than what you might expect. I think most of you have encountered the Standard Model before in coursework, in papers, and the like, and are probably relatively familiar with it, and I'm not sure there's a great deal that I could add in that sense. On the other hand, what I can do, and I think what I'm more adept at, is providing a somewhat idiosyncratic approach to introducing some of the ways in which practicing particle theorists think about the Standard Model. And that means that over the course of the next 3 lectures, we're going to spend more time on why rather than what or how. But that doesn't mean we won't have any of the how in particular. But what I hope to do is, as quickly as possible, get to a point of view, one shared by most practicing particle theorists, which allows us to at least ask what the big questions are in particle physics today, what the shortcomings are in the Standard Model. Not surprisingly, all of you in your careers are going to spend 99% of your time considering those shortcomings, because the things that we know well about the Standard Model are not contemporary research topics. So having said that, I think that you may find that we start out in a way that seems a little bit slow. Bear with me. I'm trying to establish a common language, one in which we can use to communicate with that very odd community of idiosyncratic people working on the shortcomings and extensions of the Standard Model. So I want to start in what is often really the first place that any student who encounters the standard model starts with, and that is a simple calculation, and that is the muon lifetime. So even as an undergraduate, when one first learns about the muon, you are taught that there is a simple primary decay mode of the muon. A particle which you are probably taught is a heavier copy of the electron. We'll explore what that means in some detail later. However, unlike the electron, it is unstable, decaying into an electron, an anti-electron neutrino, and a muon neutrino. And often one encounters a picture, a stick figure, which looks something like this, with the muon on one side, the muon neutrino, the electron, and the anti-electron neutrino on the other side. You are then taught that you should take a Lagrangian, which involves a new constant of nature known as Fermi's constant, capital G sub f, and a product of two somewhat peculiar looking currents. And in an orgy of notation, the mu index here is not a index which is summed over. It implies the muon, and similarly the E here implies the electron, whereas the alpha is indeed an index that is summed over the relativistic variables 0, 1, 2, and 3. And the currents take this odd form. I'll write the one for the muon, nu bar mu x, gamma alpha 1 minus gamma 5, mu of x. And I'm sure all of you have seen this before. And what we are told is that, for example, this mu of x is a field that annihilates a muon and coincidentally creates an anti-muon, and similar statements for the other fields that appear in these currents. The muon antineutrino field, and then the fields that reside in the electron current. Okay, so after some few lectures showing this, you are taught a bunch of rules that allow you to evaluate the quantum mechanical transition amplitude in lowest order perturbation theory, square it, sum and average over spins, integrate over phase space, and eventually obtain the very famous formula that the transition rate for the muon to decay is the muon mass to the 5th power divided by 192 pi cubed times this fundamental constant, the Fermi constant squared. Okay. So there we go. That's the first encounter most of you have probably had with the standard model, and for decades, this was the standard model. And if we were living 60 or 70 years ago, this would probably be the end of my lecture. But today, this calculation raises a variety of fairly obvious questions. So first, what do we mean when we say that mu of x is a field that annihilates a muon? I'm out of practice. I can't write very fast. And secondly, why did we pick this particular Lagrangian? Where did it come from? And especially given that I think all of you know that this Lagrangian is no longer what we call the standard model, why did anyone use it? And why do we think that this calculation of the muon lifetime has any validity at all? Okay, and although those questions may seem a little bit simplistic, it turns out that understanding the answers are actually quite deep and provide enormous insight into the way we think about the what we call the standard model today. So what I really want to do is, with that as an introduction, to try to answer those questions, I want to go back really to the beginning. And that means I need to talk about the fundamental framework which we use to construct both the standard model as we currently understand it and the Fermi theory of the standard model that Lagrangian I just wrote, by going back to quantum field theory, that fundamental framework, which arises really just by trying to combine relativity with quantum mechanics. So what I want to do is, in the course of maybe 5 or 10 minutes, review everything there is to know of quantum field theory. Not surprisingly, I'm going to have to leave a few things out. So we're going to start by just reminding ourselves about how quantum mechanics works. So by that I mean specifically when we encounter a new quantum mechanics problem, how do we proceed? Well, quantum mechanics really is a theory of observables represented as linear operators that act on a Hilbert space. So observables as linear operators on a Hilbert space. And so when confronted with a new physics problem, we have to do two things. What Hilbert space and what operators? Now, there is a third thing which I didn't mention, which is time evolution, the dynamics of the system. Having identified the Hilbert space, having identified the operators corresponding to observables, we also like to know how everything evolves with time, and that's given by a Hamiltonian. And together, those three things constitute the solution to any physics problem in the context of quantum mechanics. Okay, so as an example, without relativity, the answer to this is extremely straightforward. Without relativity, typically we are talking about what is often called single particle quantum mechanics, and the operators are all the polynomials we can construct from the momentum p and a position q. And that constitutes everything that can be observed about the system. For the Hilbert space, well, usually we take either position or momentum eigenstates as a basis. And then we define the Hilbert space as the completion of all linear combinations of those basis states. Okay. Finally, adding a Hamiltonian to the system is what distinguishes different non-relativistic quantum mechanical physical problems. If we're talking about a harmonic oscillator, for example, we have a single p, a coarse q, and a Hamiltonian, which is just some quadratic form in p and q. If we're talking about, oops, really? Oh, I think you are correct. Can you still hear me?
Yes. Yes.
Okay, you can hear me, but the screen is frozen. That's not good. Still frozen?
Yes. Yes.
Okay, let's see. Let's try that again. Okay, am I visible again?
Yes.
Excellent. Okay, and this is working. You can see this. You're getting dizzy now? Yeah?
Yes, yes, yes.
Okay, very good. Sorry about that interlude. Okay, so Non-relativistic quantum mechanics, easy. Observables are P's and Q's. Hilbert space starts with position or momentum eigenstates as a basis. You complete linear combinations, and you introduce a Hamiltonian, which includes whatever dynamics you want for P and Q. With relativity, we already suspect that we're going to need something beyond this Hilbert space and beyond those simple operators as P's and Q's. The problem arises because of really the most basic elements of relativity. We can see this by starting with a simple thought experiment. If we try to localize a single particle by putting it in a box of smaller and smaller size, well, we know that according to the uncertainty principle, the smaller we make that box, that is, the better we localize the position of the particle, the more uncertain its momentum is. Or in particular, it means that the better we try to localize the particle, the more we must include momenta that are large. So if we imagine trying to localize a particle to a size which is smaller than the Compton wavelength of the particle, in order to do that, we're going to need momenta, which are then much larger than the Compton wavelength, which in natural units is just the mass of the particle that we are trying to localize. But of course, given the usual dispersion relation, the energy-momentum relation, large momentum, P, implies a large energy. That is, if we try to localize a relativistic particle to a size which is small compared to its Compton wavelength, we will necessarily be involving energies which are much, much larger than the mass of that particle. But famously, in what is probably the most famous equation in all of physics, there is a relationship between the energy and the mass. More precisely, in relativistic systems, mass is not a conserved quantity. That is, mass is not something that is invariable during any kind of dynamical process. On the other hand, the energy is. The energy remains conserved in relativity, even though the energy is not. Consequently, if we start with a single particle with a mass m, in relativity, there's no particular reason to expect that when we try to involve modes with energies that are large enough, that is to say larger than 2m or 3m or 4m, that we remain with only that single isolated particle. In particular, we expect that if we try to do this localization in practice, maybe we take a proton and we start using electric and magnetic fields to confine that charged particle to a size which is much smaller than a Fermi, the Compton wavelength of that proton, well, inevitably, we are going to, because of relativity, discover that when we do that, we start creating lots of new particles added to the state. The same is true even if we try to do this with an electron, where we would discover that the consequence of trying to localize that particle to a tiny region is that we're going to create lots of new electrons and associated positrons. So from the experimental point of view, it's clear that when we try to localize relativistic particles, we don't remain with only single particles, but we now have multi-particles that we have to deal with as well. From a conceptual point of view, we're not surprised that that happens just because in relativity mass is not conserved. So right from the beginning, when we're dealing with a relativistic problem, we should expect the Hilbert space should involve not just single particle states, but multi-particle states as well. And although this might seem like a rather small change from the non-relativistic case, in fact, it is an enormous one. So right to begin with, in answering those questions about how we deal with quantum mechanics for a system, the answer to what is the Hilbert space is that it should be the Fock space. So the Fock space consists of all the states. So there's a set of states which have single particles with a definite momentum k. There are states which have two particles with definite momenta k1 and k2. There are states that have n particles with definite momenta k1 through kn, etc. And in addition, we should then allow also for the special state that has no particle in it, and therefore is not labeled by a momentum, which I've just indicated with a 0 here. Of course, in specifying the Hilbert space, we also have to specify the inner product. I'm not going to bore you with the details, but it's the usual way that states with different values of the momenta are distinguishable, and therefore their inner product should be 0. Because we're in a continuum, this is given by a direct delta function. And then there's a conventional normalization of this thing that I'll call 2 omega k, where omega k is the square root of k squared plus m squared. You don't have to put that in, it just is common to do so. Of course, similarly, for multi-particle states, we have the same thing, that this matrix element should vanish if we can distinguish them. So if k1 is not equal to k1 prime and k2 is not equal to k2 prime, then it should vanish. Well, with one minor caveat, of course, it could be that k1 is equal to k2 prime and k2 is equal to k1 prime. So are we frozen again? Are we back?
Yes.
Thank you. Okay, we will try to figure out how to fix this in the future. Okay, so we have our Hilbert space now, but we still need to ask what the observables are. And in addition, we need to ask about dynamics. Well, in fact, it's easier to ask about dynamics for free particles, so we'll start with that before we talk about observables. For a free particle, well, if we had a single particle, the Hamiltonian would simply be, would simply be the energy of that particle. And therefore, if we have a multi-particle state, if they're free, then we just add up the energies. By the way, of course, this is just the thing I introduced as omega k to make life easy. Okay, so the dynamics of this system is very simple. The Hamiltonian is very simple. Of course, since we're dealing with relativity, we expect that really there should be a combination of the Hamiltonian with the 3 momentum to make a 4 vector. P mu, still an operator on the Hilbert space, where in general, acting on the Hilbert space P mu on the n particle state is just the sum of k mu acting on the state. Okay, so we've done the Hilbert space, we've done the dynamics, but we're missing the most important part, which is, what are the observables? So in order to construct the observables on this system, it's common for us to introduce a certain notation. it is a convenience to make it easy for us to keep track of things. In fact, if we think about all the possible operators on the Hilbert space, what can they do? Well, any operator we can think about, maybe it changes the momentum. That's sort of an obvious thing we could do. But we can also change, we can have non-zero matrix elements between states that have different numbers of particles. So if we want to try to construct arbitrary operators on this Hilbert space, from which we will select those that are interesting physical observables, it's convenient to have a set of operators that act very simply in just adding or subtracting one particle from any given state in the Fock space. So we introduce an operator A dagger of k. That is, we introduce one of these operators for every possible value of the 3 momentum. And we define it so that, let me actually call it A of q, that acting on the n particle state, it adds a particle of momentum q. Okay, from the inner product that we defined before, I'm sorry, so it is conventional to call an operator of this sort a creation operator. Seems reasonable since it's adding a particle to the particular state. Notice at this stage, there's no physics here. I'm just doing this as bookkeeping to make it easy in order to keep track of the operators that we are about to construct. Okay. From the inner product, if a dagger adds a particle to a state, then A must remove a particle from a state, and hence we call A an annihilation operator. Okay, from everything I've said, it's a matter of seconds to compute the algebra, the commutation relation for these operators, and the different A and A daggers commute unless their momenta are the same, in which case they have a commutation relation, which is basically the continuous analog of 1. That is to say, the A and the A dagger behave like the raising and lowering operators of the simple harmonic oscillator. Okay, that's it for all the annoying notation. So I'm now going to make some statements about this setup that we have. We have a Hilbert space, we have a Hamiltonian. Our job now is to construct the observables. It's not hard to show that every linear operator on the Fock space can be constructed out of the operator A hat and A hat dagger that we just introduced. Okay, so that's why I introduced them. We can make anything at all. But the challenge is to figure out what the actual observables should be. So given this freedom of constructing anything with A and A dagger, we're going to have to impose a few conditions in order to help us identify what the actual observables on this system should be. Note that you might have thought that, well, shouldn't we be just doing what we do in non-relativistic quantum mechanics and identifying the position observable? But notice that we run into trouble right away. If we say that we want to construct a position observable, well, the position of what? When we have a single particle, we know exactly what we mean by the position of that particle. But remember, we've argued that we needed to introduce the Fock space. So we don't only have states with single particles, we have states with many particles. And through the dynamics of the system, we expect that even if we start out with only a single particle, we will inevitably evolve in ways that allow creation of new particles. And consequently, the meaning of position is already quite obscure. Position of what? The initial particle we started with? All the new ones that have been created? Maybe the center of mass of the whole thing? But it's clear that we already have a challenge ahead of us and that we're not going to be able to follow the same naive path of constructing a position operator. So in fact, by thinking again about relativity, it's not too hard to figure out a path forward. So we've already included one of the most famous features of relativity, that the mass is not conserved, but is a contribution to the conserved energy. But another crucial aspect of relativity is the causal structure, that relativity has events. An event really just means a location in space and time. So a point in space-time. That's all we mean by an event. It is a location in space-time at which something might happen. Famously in relativity, there is no possibility of communication faster than the speed of light. Consequently, the causal structure of space-time, the set of all these events, is not as it is in non-relativistic physics. There are points in space-time that are causally disconnected. That is, we can have two events that can have no communication between them. It's simple. If there's no possibility of some communication at or less than the speed of light between those two space-time events, there's no possibility of any influence of one event on another. For example, if we agree to synchronize our watches so that we know we're reading the same time, and then we agree to choose a piece of fruit to eat at noon tomorrow, I may choose an apple or an orange, you may choose an apple or an orange. There is no way sure that if we choose at random, there's no way for me to communicate to you what my choice is if we agree to do it at the same time, because that would require a signal to be sent from me to you faster than the speed of light, which is forbidden. So, in fact, this is a profound and unique feature of quantum mechanics with relativity, that when we start talking about observables, famously, a measurement in one system can affect subsequent measurements. We all know that if we try to measure the location of a particle, immediately after that measurement, which returns a definite value for the location, the momentum is undetermined. Or if we try to measure the component of a spin, and we measure it to have a positive spin in the vertical direction, then we have disrupted the possibility of measuring with definite answers different components of the spin. So if we know that observables correspond to linear operators, and those observations might correspond to things that take place in causally disconnected regions of space-time, it must be the case that those measurements cannot influence each other. So this whole business about the measurement disturbs the system cannot be true if we're talking about things that are causally disconnected. And that means that if we make a measurement, the observable corresponding to that measurement had better know where in space-time the measurement happened. How else can we tell whether or not that measurement could influence things at other parts of space-time? So this, right from the start, tells us that the kinds of observables that we can choose for our system are very different from non-relativistic systems. They must know their space-time location. Observables are associated with space-time locations. So position, what we used to think of as an operator in quantum mechanics, is no longer an operator in relativistic quantum mechanics. It's a label. It's something that is attached to observables, exactly as time was a label. Even in non-relativistic quantum mechanics, when we said we wanted to measure the position or the momentum or the spin or some other degree of freedom, in the Heisenberg picture, we always talked about when we were making that measurement. It was the momentum at some time t. It was the spin at some time t. Well, not surprisingly, in relativity, where t is one part of the labeling of space-time, position being the other part, that time and space go together. So x, the position, has been demoted from its place as an operator that can be measured in non-relativistic quantum mechanics, and it has become on a par with t, simply a label for operators. It's not particles that carry position, it's the observables that carry position. Okay, so once we appreciate this extremely profound fact, it's actually not very hard to construct the observables that we are after. So as I said a few minutes ago, we're going to have to impose a few conditions in constructing them. But we already know that one of those conditions is observables are going to carry a space-time label. So let's start writing down the conditions. So the first thing is we know that true observables correspond to Hermitian operators. We want them to have real values when we measure them. So we will demand that our observable, I picked one particular observable, phi of x. Of course, there will be many observables. We'll talk about the others in a minute, but we'll start with one. But whichever one we pick, we know that it must be Hermitian. We also know about time evolution. Well, time evolution we can think of as translation forward in time, and we know that that's generated by the Hamiltonian. In a relativistic system, in addition to motion forward in time, that is a translation in time, because of relativity, we must also have translations in space. Those, of course, are generated by the three momentum. Together, that means we have space-time translations, which should be generated by the momentum operator, which we've already introduced. So, as a technical thing, if I make a translation on our observable by a distance a, we know what we want this to do. Remember, the x label on phi was saying that phi of x corresponds to some observable, some measurement done at the space-time location x. If I do a translation by a, then I should get the corresponding observable, but now at the space-time location translated by a. By the way, something I forgot to say at the beginning is that you should feel free to interrupt and ask questions as we go along. That's probably more effective than waiting until the last 10 minutes and discover that you had a question based on the second thing I said. So by all means, feel free to interrupt me. Since I can't see you, you either are going to have to scream it out at me or use the chat box. Okay, so a technical thing that I'm not going to waste any time on is, just as we have space-time translations, of course, we're dealing with a relativistic system, so there should be Lorentz transformations. We will talk a good deal more about Lorentz transformations a bit later today, but that means there should be operators corresponding to Lorentz transformations that should have the effect of, again, changing the space-time location. If we make a Lorentz transformation, we transform certain space-time events into other space-time events, and therefore, under this transformation, we should take a measurement at space-time location x and relate it to a measurement made at the Lorentz transformed space-time location. The details here are not important. Why it's lambda inverse, that's a convention. But basically, this is the same as the translation, just corresponding to Lorentz transformations. Okay, next, we come to, by far, the most important thing, and the real reason why we embarked on this discussion in this way. So phi of x corresponds to some observable, some measurement we can perform at the space-time location x. Phi of y corresponds to the corresponding measurement, but made at a different space-time location y. Now, as you know, whether or not two measurements interfere with each other quantum mechanically is related to whether or not those measurements commute. If the measurements commute, it does not matter whether one of them got performed before the other. And therefore, they would have no influence on the outcome of the other measurement. Well, we have just argued that the reason that all of our observables must come attached with a space-time label is because they must be able to tell whether they can influence other measurements or not. Translating that into an equation, it says that if I have a measurement at space-time location x and a measurement at space-time location y, they cannot interfere with each other if x and y are causally disconnected. That means the corresponding observables must commute whenever x and y are causally disconnected. In fact, the condition that they are causally disconnected has a nice, simple statement in relativity. It is when the difference in space-time locations is a space-like 4-vector. That is, where the square is less than 0. So recall that the square is of a 4-vector is the space component squared minus the time component, the time component squared minus the space component squared. So being negative says that the spatial separation is larger than the time separation, which means a signal traveling at the speed of light, which is 1 in these units or less, can never get there in the time interval. So this condition, number 4, is sometimes called microcausality. And note, it is a condition on observables. It is a statement that the only observables we are allowed to keep are those that satisfy the microcausality condition. Okay, I'm going to impose one other condition which is a bit less natural than the others, is I'm going to assume that our observable phi is only linear in that creation and annihilation operator. Now, you recall I said a minute ago that any operator on the Hilbert space, any linear operator can be constructed out of A and A dagger. That necessitates including polynomials in A and A dagger, A squared, A cubed, A dagger, things like that. For simplicity at this point, I am going to only restrict my attention to those observables that can be constructed linear in A and A dagger. It turns out this restriction is actually unnecessary. Once we have constructed the observables linear in A and A dagger, all other observables follow simply. Okay, so now I'm not going to do it because it would take about 10 minutes, and I don't want to waste the time. It turns out these conditions uniquely determine the observable. So I suspect that many of you have seen, or sorry, many of you recognize immediately this form, although you probably arrived at it in a different way. So let me first recap how we arrived at this. We decided what our Hilbert space had to look like, the Fock space, including multi-particle states. We constructed the appropriate Hamiltonian, or really the four-momentum four-vector. We then started to consider the properties we wanted our observables to have. And we immediately realized that observables had to be operators that were labeled by space-time location. We then demanded that they be Hermitian, that they satisfy appropriate properties under space-time translations and Lorentz transformations, that they satisfied microcausality, and linear and A dagger, and we got a unique answer, which was this quantity here. But as I said, this is probably not how most of you arrived at this formula in traditional quantum field theory texts. So I want to turn this around for a minute. You can easily verify the following approach. If I start with an object, a field, that is to say, an operator that depends on space-time, and I demand that it be Hermitian, that it satisfy the Klein-Gordon equation, a partial differential equation. If I demand it satisfies the Heisenberg canonical commutation relation. So remember, the canonical commutation relation says that the commutator of P with Q is minus I. So the momentum is the time derivative of the position. So I have taken here the observable and its time derivative, which should be the canonically conjugate variable. And I've constructed the commutator at equal time, and I've set it equal to minus I, which is the Heisenberg canonical commutation relation. I, of course, have a delta function just because I'm dealing with the continuum, so that this vanishes when x and y are not equal, and has an integral which is 1. Finally, if I demand that phi of x as a field is a scalar under Lorentz transformations, okay, it's not hard to show that if I take these 4 conditions, they imply exactly the same decomposition of...
Sorry, I think it froze because we can see only...
It froze again? Okay,
maybe,
hang on.
Maybe you can switch off your camera because I think your connection is not good. So you are splitting the bandwidth with 2, but maybe you can put your screen and then switch off your camera. Let's see whether it...
Okay, my camera is off.
And we can see now 3 conditions because the screen is not low enough, but I think it will work. Okay, there we are.
Okay. Okay. Once we get through this first lecture, I'll play with it and see if I can fix this problem. I have another camera around, so okay. All right, I was reaching the punchline. So I think I have a question from Omar. Is that true? Omar, can you unmute and say something?
Yes. Can you hear me?
I can.
Okay. So the question is about, let's say, this quantum field theory formalism. As you said, one of the ingredients to obtain this field expansion is the Klein-Gordon equation. But this equation, let's say, appears, I think, historically from trying to obtain, let's say, a Schrodinger equation with a relativistic energy. But I don't know, I think there is where, let's say, everything is set up. But let's say someone wants to start another formalism, which is for describing particle physics, which is not based on field theory. Let's say someone wants to generate another thing. Then how can they start?
Okay.
I mean, if
yeah, Omar, let me interrupt you. So this is, so let me, okay, I'm going to do two things. So first, I'm going to postpone your question for a little bit because we're going to come back to it. Okay, but let me make a comment before I postpone you, which is it is extremely important, and I have a lot of comments about this later, to forget about history. Okay, forget about everything you ever heard about the Klein-Gordon equation arising as an attempt at producing some kind of Schrodinger equation satisfying Lorentz dispersion, all of that. Do you want to know why I encourage you to forget about that? Because it's all wrong. You know, one of the challenges with dealing with new physics is that the way we get here is filled with errors and incorrect logic. And over time, we begin to learn the right things, but frequently we continue to teach it in the wrong way. So part of the reason why I'm going through all of this stuff that you've seen before is to show you how we now understand it. There's no connection with a Schrodinger equation. Okay, that's just an error. That is actually before people understood that you need to introduce the Fock space. Okay, so for the purposes at least of these 3 lectures, maybe you don't believe me about history being all wrong, but for the purposes of the 3 lectures today, do me a favor, put all of this stuff you heard before out of your mind, and we will talk about the parts of it that turn out to be wrong and exactly why they're wrong. Okay, so that now I'm going to put you off because you started coming to a different approach saying maybe there's an approach to all of this which is not quantum field theory and something else, and we will talk about that shortly. Okay? Are you?
Okay, so almost. So then that comes to the question I wanted to ask, because I don't see how, let's say, you can obtain a very general formalism without premise number 2, which is the Klein-Gordon equations. I cannot see where that comes from. I mean, usually we start with a field and we try to find appropriate field that transforms under certain Lorentz representation.
Okay, Omar, all right.
Okay.
Omar, hang on. Okay, let me get 2 more minutes in, and then we'll have this conversation, okay?
Okay, thank you.
You just wait 2 minutes. Okay. So I'm going to come back to what I was saying, and I'm going to actually repeat it. So what did we do? We started with the Fock space, some general principles, and we're inevitably led to this observable. I'm now simply making observations about this observable. I am not adding any new content. You can check immediately that this observable has the 4 properties that I've listed here. It is Hermitian. It satisfies the Klein-Gordon equation. I am not introducing the Klein-Gordon equation. I am encouraging you to simply act with these differential operators on the phi that we wrote earlier and see that it satisfies that equation. You can use the commutation relations we wrote down earlier, the A and the A dagger, to verify number 3, that it satisfies the canonical commutation relation. Finally, it's actually a tautology that it's a scalar under Lorentz transformations because we constructed it to be that way. Okay, I am just saying you can verify these things. And by the way, you should do so. You should take a few minutes later today and verify that it satisfies these things. So why am I telling you that it verifies these things? Notice I did not put these things in. I didn't start by saying we're going to have a Klein-Gordon equation. I did not start by saying we're going to have a canonical commutation relation. What did I start with? I started with, what's the Hilbert space? I argued that on the basis of relativity, we were almost certainly going to have to include multiparticle states, so I talked about the Fock space. I introduced an appropriate relativistic Hamiltonian and associated three momentum. And then I constructed observables satisfying some simple basic criteria. They had to be Hermitian, they had to transform correctly under Lorentz, they had to be labeled by space-time position in order to satisfy microcausality. And I ended up with the decomposition that we saw a minute ago, right there in the box. And then I pointed out they satisfy these four things. Okay, is that logic clear? Nod your heads. I can't see it, but I'll assume you're all nodding. And now, here's the point. I can reverse this process. I can turn it around. I can start without ever talking about a Hilbert space, quantum mechanics, or anything. I can say, imagine I have a classical field theory with a classical scalar field phi that satisfies the Klein-Gordon equation. And now I simply want to use the canonical procedure to quantize that classical theory. What I've just shown you is the outcome of that process is the decomposition of the observable in terms of creation annihilation operators, the Hilbert space, the Fock space, and the Hamiltonian. Okay, and this is now the punchline. This is our first big result. The Fock space plus local observables this was physics. Let me be clear about that. This was not math. The Fock space we argued on the basis of physics, that relativity conserves energy but not mass. The local observables we argued on the basis of physics. Causality requires the observables to have space-time labels, and they must commute at space-like separation. What we have shown is that we get the same output. Canonical, I forget how to spell. If we canonically quantize a scalar field with the Klein-Gordon Lagrangian. That is math. Okay, so I'm a physicist. I think all of you are physicists as well. The physics is what drives this. It's the Fock space plus local observables. We followed that path and discovered that we would have gotten the same output if we had solved a math problem. The math problem is the canonical quantization of the scalar field with the Klein-Gordon Lagrangian. But there's no physics in that starting point. There's no argument that, oh, we want to do that because it's going to look like a Schrodinger equation or something. Get that. We did the physics correctly. Fock space plus local observables. We have now made the very important observation that we can arrive at the same result by solving that math problem, the canonical quantization of a Klein-Gordon scalar field. In fact, it's not hard to see that the same thing works for any Fock space, even if we're including particles with spin. That is, given a Fock space and local observables, we can find a field theory whose canonical quantization will lead to that Fock space. So it is commonplace to start now with the field theory because we know, not because we like that field theory, we think there's anything special about that field theory, but because we know how to identify which Fock space and which local observables are going to arise from it. It's a convenience only. Okay, Omar, are you ready to come back?
I'm ready. Okay, so
okay.
I think it's a
okay, wait. Don't talk yet. I just want you online. Well, we have a conversation now, but I have a few more things to say. So what I'm trying to say clearly, I hope I've said it, I'm just going to say it once again. We start with the physics. We discover that the answer to our physics problem is the answer to a particular math problem. It's more convenient as a bookkeeping device to talk about the canonical quantization of the fields rather than always writing those complicated expressions with the Fock space. But we do it because we're really talking about the Fock space and local observables. That's number one. Number two, what's special about local fields, the observables with their space-time locations attached, and why that leads to the quantization of these fields, is because it gives rise to the Fock space in a way that can ensure the relativistic invariance, because we can impose relativistic invariance in a straightforward way on the field theory. Now, by the way, there's a slight subtlety here which I didn't talk about. There's a property called cluster decomposition, which is quite important and also is part of this discussion. The canonical quantization of the field theory guarantees that our observables will have this property of cluster decomposition. Okay, Omar, your turn.
Okay, so I like very much the approach you took, but I still feel that you inputted the Klein-Gordon equation. I think I can pin it down. It was when you defined how the momentum operator should evolve the field. So I think there you are inputting Klein-Gordon equation in some way. Everything is very general, yeah. But
okay. So good. Let me answer that. Stop. Okay. So you are both correct and incorrect. Okay. I did not impose the Klein-Gordon equation. And let me be very clear about that, and I'll prove to you I didn't impose the Klein-Gordon equation. It turns out to be true, but it is not because I chose that Hamiltonian. So first of all, the Hamiltonian I chose follows entirely from relativity and the fact that it's a free particle. I'm sure you do not disagree that the energy of a relativistic particle is the square root of its 3 momentum squared plus its mass squared. Do you dispute that? Say no.
No, I don't. I agree.
Okay. And I'm sure you don't dispute that if I have 2 such particles and no interaction between them, their energy is the sum of those 2 things for each particle. Do you dispute that?
I agree.
Okay, so I made no assumption beyond elementary relativity from the early 20th century, nothing about Klein-Gordon, blah, 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 okay? If it turns out to be equivalent to the Klein-Gordon, I still did not input Klein-Gordon, it's an output. That's number one, okay? And I'm sure you agree with that. But let me point out, it is not the Klein-Gordon equation. Notice the Klein-Gordon equation, as a linear operator, would say that if you act on objects which have 2 different lumps, then the momentum is the sum of those 2, and you square that. And the energy is the sum of those 2, and you square that. That is, the time derivative gives you the sum. Okay, so as you can see, the Hamiltonian is not the square root of the 3 momentum operator squared plus m squared square root. Or let me say that slightly differently. Actually, let me write it down so you can see it. The Hamiltonian squared is not the momentum squared plus m squared. This is not true. If you act on a single particle state in the Fock space, it is true. But acting on the multi-particle states, it is not true, as you can easily verify. Because the energies sum. They don't add in quadrature. Okay, so the Klein-Gordon equation would look like h squared as an operator minus p squared as an operator is equal to m squared, which is false. Okay, I'll let you stew on that for a while, but it is not the Klein-Gordon equation, and no, I didn't put it in. Okay, now I want to come back to your other question, which is very interesting, which is quantum field theory inevitable? Assuming I want a Fock space, I want local observables, and all that physics that we put in, is quantum field theory the only way to do it? What I've said so far is quantum field theory inevitably leads to Fock space plus local observables, which is good. But the question is there something else that's not quantum field theory that would also lead to Fock space and local observables? That would be very exciting. The answer is actually unknown and is an active area of research. So you've probably heard at least some of the words associated with that avenue of research. There's something called string theory. You've heard of string theory, right? I'll assume that you said yes, okay, or you're shaking your head. You've heard of string theory. String theory was initially assumed to not be a quantum field theory and yet lead to Fock space and local observables, and therefore has a chance of giving us the physics that we're interested in. If that's true, then we have an example of something that is not a quantum field theory, but leads to Fock space plus local observables, which is what we think nature looks like. Now, okay, so why am I not saying we already know there's a counterexample? Because research over the past decade or so in string theory has opened the door for string theory to actually just be a quantum field theory. Okay, and this is a big part of contemporary research in string theory. It's not known today. I cannot tell you the answer, whether string theory actually can be formulated as a admittedly very complicated quantum field theory, or whether it is something fundamentally different. Okay? Still with me, Omar, or have I destroyed you?
No, I'm still with you, but we can discuss it.
You're still here. Okay, good. Okay. We can have more conversation about this, but I think that we should move on because time is running late. Okay, but I'm going to pause very quickly to ask, are there any other questions? Now is a good time.
Hello, sir. I have one question.
So Argyachit, is that right?
Yes, sir. Yeah. So regarding this h square not equals to p square plus m square. So
yes,
is it not? I mean, this p operator should be like p1 square plus p2 square for different states. So eventually, this relation is true, right? Or am I missing something?
No. Okay. Okay. Hang on. Let me just show you trivially it is not true. Okay. So let me consider a two-particle state with momenta k1 and k2.
Okay, sorry, sir. It should be two p1, p2 type of things will be there. Are you trying to say this? I mean, p1 square plus p2 square plus 2p1, p2?
Yeah, so I'm saying that, yes. So I will point out that p on this state is k1 plus k2. We agree on that, yes?
So, yeah, I got what. Yeah.
Okay. So p squared on the state is k1 plus k2 squared. You agree with that?
Yes, sir. You don't have to do that. I got.
But you got it. But h
yes.
is not okay.
Equals.
So this as an operator relation is simply not true. Okay, you got it?
Yes, sir. Yeah.
Okay. Other questions? Is that it for questions? Shall we move on? We're running a little bit behind. Okay. Can you help me? Is my screen still visible?
Yes, it is.
Yes, it is. Thank you. Okay. So, all right. So far, aside from some words and some philosophy, we haven't done all that much, although we've established some notation. But believe it or not, what we've done so far already is incredibly powerful, and we can get some significant physics mileage out of this. So I want to do a simple example, something that you all are familiar with, you know the answer, but you probably haven't seen it done in exactly this way before, and it will turn out to be crucial in understanding the standard model. So I want to start by asking a simple question. For this example, I'm going to choose a non-relativistic question. Now, I just made a big deal about how different things are because of relativity and all of that, but bear with me. I'm choosing to do a non-relativistic example because it's a little bit simpler technically. We can do everything explicitly and it won't take more than 5 or 10 minutes. So the question I want to ask is one that was asked a long time ago and completely solved in the mid-19th century. The question is, why is the sky blue? So I'm sure all of you have heard this story and you know that this question was answered correctly in 1871 by Lord Rayleigh. By the way, there were lots of other famous physicists who also answered this question around the same time, but they answered it incorrectly. He's the first one who got it right. So what did Lord Rayleigh do? He used the then very new electromagnetic theory, the Maxwell equations, to calculate the scattering of electromagnetic waves from small dielectric spheres. He, of course, had no idea what the atmosphere was actually composed of. He did not know about molecules, but he did know, in part because of the kinetic theory of gases, which was in vogue at the time, that it was almost certainly composed of tiny little particles. He assumed if they were small dielectric spheres, they would scatter the electromagnetic waves, and that scattering might give an explanation for why the sky is blue. Of course, his calculation of the scattering of electromagnetic waves from small dielectric spheres is a textbook exercise now in graduate E&M courses. But we can do it with quantum field theory. Okay, that sounds like kind of an abuse of technology, like, you know, buying the world's fastest Ferrari to drive to the grocery store. But it turns out it's much easier to do this with quantum field theory than it is to do it the way Rayleigh did. So, what's the process we're interested in? Well, we know that the atmosphere is composed of molecules, primarily nitrogen molecules. And we're interested in the scattering of electromagnetic radiation, to us quantum physicists known as photons, off of those nitrogen molecules. Of course, it's really a single interaction. We only have to do one scattering at a time, so we have a single nitrogen molecule. We have a photon which comes in, scatters off of the nitrogen molecule. The nitrogen molecule recoils very little because it's so heavy, and the photon comes out. So how are we going to use quantum field theory to describe this process? So, of course, the photon is easy. You all know about QED, and you think we're going to now have to suddenly jump into Schwinger's classic discussion of how you quantize the electromagnetic field and all of that. But let's put that aside. What about the nitrogen molecule? How are we going to include that in quantum field theory? Well, these are lectures on the standard model, so you're probably thinking I'm going to start with quarks, and I'm going to show that that confinement occurs in QCD, and that the quarks get bound up into nuclei, and there's a residual force due to pion exchange, which binds the nucleons into the nucleus, and then there's electromagnetism, and you have electrons surrounding the molecule formed from two. Okay. This sounds kind of crazy, doesn't it? How come Lord Rayleigh in 1871 was able to answer this question without knowing anything about the standard model or QCD or quarks or the bound states and all of this stuff? And it's worse. If you think that we somehow need to know the standard model, quarks, gluons, and all that to do this, what if the standard model isn't right? What if it is string theory out there? Does it mean that we can't even answer the question why the sky is blue if we can't discuss string theory? Well, fortunately, as you know, none of this is relevant. Well, let's come back to that first example we did earlier today, Fermi's theory, his standard model calculation of beta decay, the decay of the muon. How could that possibly get the right answer? Doesn't he need the full standard model? Didn't he have to wait for Glashow, Weinberg, and Salam to figure out how the weak interactions work? Well, of course, you all know the answer. None of that is relevant. So why is it not relevant? Well, let's think a little bit about something simpler. how do we get the energy levels of the hydrogen atom? You all did this as probably one of your first exercises in undergraduate quantum mechanics. When you did it, you didn't worry at all about the structure of the nucleus. None of those questions arose. That's because, as you well know, the nuclear size is about 10 to the minus 15 meters, a few times 10 to the minus 15 meters. But the atomic size, which is set by the Bohr radius, is about 10 to the minus 10 meters. And the electron, in its quantum mechanical state, is spread out over a region which is the size of the Bohr radius. And because its wave function is spread out over such a large region, it's completely insensitive to the microscopic details of what's going on inside the nucleus. As far as that wave function is concerned, the nucleus might as well be an idealized point particle. In momentum space, we can say the same thing, that the atomic momentum, the momentum of the electron in its wave function around the nucleus, is much less than the characteristic momentum, and here I mean form momentum, so energy, of the nucleus, which is set by 1 over the radius of the nucleus. Remember, we're localizing the nucleus, so that means we have big momentum. This simple observation that the measurements probing long distances are insensitive to short distances, which you've been using your whole life, is at the heart of understanding quantum field theory and what we mean by the standard model. And as I said, it's really not more complicated than that you spread something out over a large distance and you're only averaging over the short distances, so you're insensitive to those fine details. So let's come back to the sky. The visible light wavelength is about 10 to the minus 7 meters, a few times 10 to the 7 meters, right? Visible light, 400 nanometers, something like that, which, notice, is much, much larger than the Bohr radius, which is 10 to the minus 10 meters. It's 3 orders of magnitude larger. So immediately, we suspect that the details of the molecule, that nitrogen molecule, should be completely irrelevant. The fact that it's actually a nitrogen molecule as opposed to a nitrogen atom, the fact that it's atoms as opposed to a point particle, the fact that those atoms have electrons and substructure and all that should be completely irrelevant. So having made this observation, it's now a matter of seconds to figure everything out. So how are we going to treat this in quantum field theory? Well, it's easy. We just have to include the appropriate quantum field corresponding to the Fock space for the nitrogen molecule. But as far as we're concerned, that nitrogen molecule is a structureless point particle. So it's the Fock space we just introduced. But it's even better, because it's non-relativistic, I don't even need the Fock space. I just need the single particle state. But it's convenient to keep the whole Fock space anyway. If we're wrong and we don't need it, well, we'll lose a little bit of time, but who cares? So what are we going to do? We're going to introduce the observable phi of x, just as we did before. Phi of x can create or annihilate a nitrogen molecule. And I don't need to know anything more than that. Now, one advantage here, which I'm not going to talk too much about, is when we impose the condition of microcausality earlier, that's what required our phi of x to include both a creation part and an annihilation part. But for the calculation we're doing now, because it's completely non-relativistic, we don't actually need that. And so it turns out, rather than a single unique observable, we can actually create one which only involves the annihilation part and another one which only involves the creation part. So I'm going to allow myself to include a phi and a phi dagger, where phi includes only the annihilation part A, and phi dagger includes only the creation part A dagger. And now we're all set. So these are the creation and annihilation. for the nitrogen molecule. Now I need the Hamiltonian. Well, because it's non-relativistic, the energy is p squared over 2m. So earlier, what we discovered is that the dispersion relation, the relationship between the energy and the momentum, showed up in that e to the ik dot x factor. Well, everything's the same, except now the energy, instead of being p squared plus m squared, it's p squared over 2m. Because of that e to the ik dot x factor, that means that that turns out to be a gradient in the field theory. So the Hamiltonian for our free nitrogen molecule is simply phi dagger minus gradient squared over twice the mass times phi. So I've left out all the steps because we don't have a lot of time, but just as we showed earlier that once we constructed the observable, it satisfied the Klein-Gordon equation, the same thing is true here. Once we construct the observable phi and phi dagger, demand that its energy is p squared over 2m, it must satisfy the Laplace equation, or Laplace equation, which means that I get the Hamiltonian here, which by a simple integration by parts is just 1 over 2m gradient of phi magnitude squared. Okay, that's the Hamiltonian. The Lagrangian is given by the usual Legendre transformation, which I won't bore you with the details. We're running late on time, but we are almost finished. Okay, so there's the appropriate Lagrangian for the nitrogen molecule. Now, because I've assumed that the nitrogen molecule was just a structureless non-relativistic particle, this is also the Lagrangian for any structureless non-relativistic system. So you see this all the time. Okay, believe it or not, the most important thing that we need in what is beginning to look like a somewhat cumbersome and complex formalism is really just the dimensions of everything. Since I have chosen natural units, h bar is 1, c is 1, there's only one primary unit, which we take to be the unit of mass. So a length is 1 over a mass, right? The uncertainty principle, delta p, delta x is h bar is 1, so p has an inverse dimension to x, you all know that. So the mass dimension of the Hamiltonian, well, the Hamiltonian is an energy, and energy is the same as mass, E equals mc squared, c is 1, so this is 1. Sorry, I got distracted there. So this is 1, and from that we can deduce the mass dimension of phi. Well, if we look at this first term, then we know that the Lagrangian is the same dimension as h, which is to say dimension 1, but then this is the d cubed x is dimension minus 3. The derivative is 1 over a length, so this is plus 1 to be equal to plus 1, so phi must be 3 halves. Phi dagger is 3, so phi is 3 halves. Okay, what about the photons? Well, we know how to include them. We know the Hamiltonian electromagnetism. It's 1/2 the integral d cubed x e squared plus b squared, which gives a Lagrangian, which is 1/2 d cubed x e squared minus b squared. And from this, E and B have mass dimension 2. Okay, you will see in a moment why I'm so concerned with mass dimensions. So we're all set. we have our theory of free photons, we have our theory of free nitrogen molecules. All we have to do is include the interaction to calculate the scattering. Okay, I see I'm frozen. We will try to unfreeze. Here we go again. There we go. Everybody okay?
Okay.
Yes, great. Okay. So we need an interaction. Well, we know what it's going to look like. I have time running up. We have the nitrogen molecule comes in. A photon comes in from the sun. The photon gets scattered out. The nitrogen molecule goes out. We need something to tell us about this interaction. So we have to figure out the part of the Lagrangian that couples the photon to the nitrogen molecule. Now, you may be thinking, well, we haven't gained anything. At this point, we have to understand the detailed electromagnetic structure of the nitrogen molecule to figure out how it's going to couple to the photons. But I have a better strategy. My strategy is to just make something up. Okay, forget about everything. Just let me write something down and see what happens. Well, I want to include an interaction that is going to contribute to this scattering process. That means I'm going to start with a state that has a nitrogen molecule and a photon. I want to do something to them, and I want to end up with a state that also has a nitrogen molecule and a photon. Of course, the outgoing nitrogen molecule and photon will have been modified by the scattering process. So I want an operator in the Lagrangian that is going to remove the incoming molecule and the incoming photon and replace them with the outgoing nitrogen molecule and the outgoing photon. So that means the thing I'm going to make up had better include a phi, which will annihilate the incoming nitrogen molecule. It had better include a phi dagger to create the outgoing N2, and it had better include an electric or a magnetic field to annihilate the incoming photon and an electric and magnetic field to annihilate the outgoing one. I also know I want it to be rotationally invariant, so since E and B are vectors, I want to dot them together. So I could have an E squared to do that, I could have a B squared to do that, or I could have an E dot B. In fact, for the argument I'm going to pursue, it doesn't actually matter which one I pick, but we do know that magnetic effects are smaller by velocity relative to the speed of light. So let's forget about the magnetic ones and just keep E squared. So I'm going to include an interaction term in my Lagrangian, which is integral d cubed x, and I'm just going to write the simplest thing I can think of, E squared phi dagger phi. Okay, everybody with me? Nod your heads. I can't see it, but I'll assume they're all nodding. Modern technology. Wait for it. There we go. Can you see it again? No? Yes, okay, great. We're almost there. Bear with me, we have another 3 minutes to go. Okay, so there is the interaction. I repeat, I made it up. There's no reason to think that this is what the interaction actually looks like. I just want to see what will happen. Well, of course, I know that there are some more things that are here. So first of all, I know that with every electric field that came about because of an electromagnetic interaction, which should be related to the fundamental electric charge. Whatever is going on in that nitrogen molecule, I don't much care, because everything in it has a charge which is E, or proportional to E. Since there are two electric fields, that means there's an E squared. So I'll include E squared. Now, I also know that the dimensions here, E had dimension 2, so E squared is dimension 4. Phi dagger phi is dimension 3. So this is dimension 7. D cubed x is dimension -3. So this whole thing is dimension 4, but Li is dimension 1. So I got to get rid of 3 mass dimensions. So there's something here which is a length cubed. And then finally, there's some dimensionless constant. I have no idea what that could be. It could be any number. It's like the Fermi constant. It tells me something in detail about the interaction of the nitrogen molecule with the photon, but I don't know. Okay, so I know I can't see you, so you're all making these terrible faces and laughing hysterically at how idiotic I am. Why am I why do you waste your time listening to some crackpot who has just written down this totally random thing? But okay, the instructor, so I now demand that you take this thing and in lowest order perturbation theory, calculate the scattering. Well, you've all had some course in field theory. You all know how to calculate this scattering. It's not very hard, but I'm going to write the answer down without any work at all. So the differential cross-section is proportional to, I am not going to attempt to get it correct to factors of 2. All of the hard work is getting the factors of 2 right, but we will not need those factors of 2. So first of all, I know that I'm going to have to compute a matrix element of the Lagrangian interaction. I'm going to have to square that matrix element. I'm going to have to sum or average over spins. I'm going to have to multiply by phase space and integrate. So I'm going to have to square the interaction once I've calculated the matrix element. So all those constant factors are just going to come through and get squared. So there's a c squared. There's an e to the 4th. There's an a to the 6th. I know that. I can even do a little bit better. Because there's the dot product of the 2 electric fields, I know that that's going to turn into a dot product of the polarizations of the photons. So in the matrix element, I get the dot product, matrix element squared, I get the dot product of their polarizations squared. So I can even tell you what the scattering is going to look like if I did it with polarized light. Of course, the sun tends not to emit polarized light, so not necessary, but I'll do that anyway. Now, finally, I can think about the dimensions. The differential cross-section, well, it's a cross-section. It has dimensions of area. That is to say, 1 over mass squared. But notice that on the right-hand side, the only thing that has dimensions is this length to the 6th power. But I want length squared. So this has to be divided by a length to the 4th power to get it right. Well, notice the only place that length comes from is in the transition matrix element of the interaction we wrote down a minute ago. And that interaction, the only length it knows about are the momenta associated with the incoming and outgoing particles. But that's easy. The initial molecule is at rest. And the photon is coming in with an energy characterized by its wavelength lambda. The only length parameter that appears in that matrix element is the wavelength of the light, and so I now know that this lambda, oops, sorry about that, this lambda is the wavelength of the light. Okay, and that's it, we're done. We have completed Raleigh's calculation, and I didn't need to do anything more than really dimensional analysis and know a little bit of simple quantum mechanics. Famously, this 1 over lambda to the 4th dependence means that the shorter wavelengths, smaller lambdas, scatter more. When we look at the sky, we look straight up. The light is coming in horizontally. It has to get scattered at large angle to reach our eyes. but the scattering proportionally favors the shorter wavelengths, hence the sky is blue. Also why when you look out towards the horizon, it's redder than if you look up. Okay. So you all got that. I'm going to turn my camera back on because at this point we're just having a little discussion. Okay, you can all see me. I'm going to stop sharing. Okay,
No,
so
we see your ceiling.
can you see me?
No, we see your ceiling. Your camera is pointing. We see your camera on. I see your
Oh,
hand.
wrong camera. Hello.
Okay.
Thank you. Sorry about that. Okay, so we got the right answer. That's fabulous. You know, you can impress your friends when you go out to the bars tonight. Oh, sorry, there's a pandemic, no bars tonight. Well, you can impress your friends over Zoom that you can calculate this thing that took Raleigh a year to do in 5 minutes. But the real question is, why did this work? Remember, I just totally made up this interaction. There's no reason to think the interaction I made up should be the right one. Certainly, it is not obviously the one that Raleigh assumed. So why did we get the right answer with this thing? Well, that's the important question. That's what we should be answering. And that's the end of this first lecture. So after a short break, we'll be back and we will answer that question. Okay?
Thank you very much. See you in 25 minutes.
Okay, so back at 6 p.m. for me, whatever that is for you. Yep.
Yes, it's exactly noon for us.
Okay.